All right, so we said that there are two ways that energy can be transferred. If energy is transferred as a result of putting something hot in contact with something cold, that heat transfer is called heat. And any other way of doing a transfer of energy is called work. Okay, so let's talk about pressure volume, what we call pressure volume work. That's the type of work that we're mostly going to be dealing with. Okay, and so PV work refers to what's called pressure volume work. Is that the last? Oh, okay. Pressure volume work. Okay. I think I have the wrong slide. Ah, here. Okay. So work, okay, is energy that's transferred due to the application of force over a distance. So the value of the work that you're doing, if you exert a force over a distance, is just the product of the force that you're exerting times the distance over which you exert it. Okay. Now we're going to be primarily concerned here with what's called pressure volume work. And that refers to the energy that you transfer between the system and the surroundings when the system either expands or contracts. Okay, when a system is expanding or contracting, what does that mean? There's an unbalanced force at the boundary between the system and the surroundings. Okay, so the amount of work that's involved there, the amount of energy that's transferred during that process of expansion or compression is equal to the external pressure multiplied by the change in the volume. So this is P external times delta V. Okay, change in volume. So we need to adopt a sign convention here. Okay, and if you have a system that's expanding, okay, if the system is expanding, it's doing work. We say, okay, it's working against an external pressure. Its energy is going to drop. Okay? If you're doing work, you lose energy, right? So expansion causes a decrease in the energy of the system. So we say work is being done by the system. So since the system is losing energy, we've adopted a convention so that in that case we assign a negative value for the work. So when a system is expanding, we say work is negative. Okay? The amount work there in that case is the amount of energy that is the amount of energy that's transferred between the system and the surroundings. Now, if you're compressing the system, then that leads to an increase in the energy of the system. Okay? And so work, for example, if you were to squeeze a gas, you're going to cause its temperature to increase because you're transferring energy to your gas. So work there is said to be done by an external force on the system, and that leads to an increase in the energy of the system. So when a system is compressed, we say work is positive. So so that the value for work that we calculate, the algebraic sign, is consistent with that notion of work being positive or negative, positive for compression and negative for expansion. Our formula for work is written this way. Work is negative, there's a negative sign in front there, times the P external times the change in volume. Okay, let's see if that's consistent. What happens if a system expands? V final minus V initial would be positive or negative if it expands? Final volume is higher than the initial volume. So this number is bigger than the number you're subtracting. So that's positive, right? So if your delta V is positive, a negative pressure is always a positive number. So a negative times of a positive times a positive will give you a negative value for work. So expansion, negative work. Compression, what happens to compression? Final minus initial volume would be a negative number, right, for compression. So that's expansion. This is for compression. And so negative of a negative number will give you a positive number. So work is positive for compression. So let's apply that simple formula to this question. Calculate the work involved when the volume of a system changes from 546 to 382 liters under a constant external pressure of 1.5 atmosphere. What's the formula for work? Negative P external times delta V What's our external pressure? 1.50 atmosphere. And what's our volume change? Final volume is, what's our final volume? 382. What's our initial volume? 546 liters. So what is this answer? Okay, this is negative, right? And there's a negative in front here, so the whole thing is positive. 246 liters times atmosphere. Positive. Should it be positive? Is the system expanding or contracting? From 546 to 382. 546 to 382. Compression. So work is positive. That means the system gained energy. So that energy transfer is classified as work. Okay? So a pressure unit times a volume unit, liter times atmosphere, is a unit of energy. So what is that in joules? You should be, you can show that 1 liter times atmosphere is equivalent to 101.325 joules. So it's a good conversion factor to know. Okay? So that's 101.325 joules. So if we want to change this to joules, what would this be? 246 times liters times atmosphere. 1 liter atmosphere is 101.325 joules. So what would that be? Times 10 to the 4th joules. Okay. So you may be wondering, how did a pressure unit and a volume unit end up being an energy unit? Think of it this way. Remember we said force times distance is an energy unit, right? Force is what? Newton. And distance is meters, right? So a Newton meter is what we call a joule, an energy unit. What if you have a pressure unit times a volume unit? What's the unit for pressure? What's the definition of pressure? Pressure is force per unit area, right? You divide the total force by the area on which it exerts, that's pressure. So the unit for pressure is newtons per square meter. Okay, what's the unit for volume? Length times length times length, so it's cubic meter. So what's Newton per meter squared times meter cubed? Newton times meter, which is a joule. Okay, so a pressure unit times a volume unit is a joule. So this pressure unit right here is called a Pascal. Okay, and that happens to be related to the atmosphere. Atmosphere, if you recall from your earlier classes, 1 atmosphere is 1.01325 times 10 to the 5th pascals. Okay, that is the pressure due to a column of mercury that is 76 centimeters tall. Okay, and you can calculate that pressure to be equal to this many pascals. So that's just to review you on the units. Okay. Let's look at this one. Calculate the heat and work involved when half a mole of liquid water is heated under a constant 1 atmosphere pressure from 10 degrees Celsius to 30 degrees Celsius. What's our Q? Remember? It's number of moles times delta H vaporization per mole, right? Oh no, this is not, we're not vaporizing, I'm sorry. we're just heating water. What's the formula for Q? Mass times specific heat times delta T. What's the mass of water here? 0.500 mole. How do you change that to grams? (18.02 grams per mole). Mole cancels out. Specific heat of water is 4.18 joules per Kelvin per gram. What's our delta T? From 10 to 30, so positive 20. Let's make this 3 sig figs there. Positive 20.0 degrees Celsius, so positive 20.0 Kelvin. So what's that Q equal to? 753 joules. All right. How about the work involved here? Work is minus V external times V final minus V initial. What's our external pressure? One atmosphere. What's our V final and what's our V initial? If you're given the density, how do you get volume from density? Density is mass over volume, right? So volume is mass over density, right? So volume final is the mass of the water divided by the final density, minus the initial volume is the mass divided by the initial density. What's the final density? That's the density, this is at 30 degrees, right? The initial density is the density at 10 degrees Celsius. So let's factor out our mass. So that's going to be minus 1.00 atmospheres. What's the mass of our water? Half of 18, right? This is the mass of water. So that's 9.01. One over, what's our density? At 30 degrees. 0.99970. I'm sorry, 99565. Grams per mil. What's the density at 10 degrees? 99970. Grams per mil. So grams are going to cancel out, and so you have your answer in mils there. What would this be? Minus 1.00 atmosphere times 9.01 times, this whole thing is going to be in mils. What's 1 over 0.99565 minus 1 over 0.99970? Calculator. Parenthesis 1 divided by 0.99565 close parenthesis minus open parenthesis 1 divided by 0.99970 close parenthesis equals, so that is 0.0040689 milliliters. Okay? So very small change in volume. 0.00400689 milliliters. So you multiply that by 9.01 times 1 atmosphere. That gives you 0.0366, so 0.0367. Negative 0.0367 liter times milliliter atmosphere. Okay? Milliliter times atmosphere. So that gives you negative 0.0367 times 10 to the negative 3 liters times atmosphere. And let's change that to joules. That's a liter. What's a liter atmosphere? 101.325 joules. So what would that be? 0.0367 times 10 to the negative third, so times 0.001 times 101.325 joules. That gives you 0.00371 joules. Okay? So what happened there? That's a negative work. Why negative? That means the water, did it expand or contract? Negative work means expansion, right? So does that make sense? Did water expand from 10 to 30 degrees? Did it become more dense or less dense? Becomes less dense. So when something becomes less dense, that means density is mass over volume, right? When something becomes less dense, that means the volume has increased. Mass doesn't change, right? So when something becomes less dense, its volume has increased. So the volume increases, water expands from 10 degrees Celsius to 30 degrees Celsius, so you have a negative work. Compare that work, though, to the amount of heat. Heat flow, in this case, is 753 joules. How much energy did it lose because of expansion? 0.0037 joules. Compare that to 700 joules, 750 joules. So for practical purposes, you can just ignore that, right? Just in terms of the total amount of energy that's involved when water is heated from 10 degrees to 30 degrees. Okay. Here's another example of a question involving work. You have a reaction occurring in aqueous solution. It gives you half a mole of gas at constant temperature and pressure. Okay. And calculate the work involved. Well, the thing about changing, producing a gas, okay, a change that produces a gas, minus P external delta V. If you remember your ideal gas law, PV equals nRT, right? Anytime you have a change in the amount of gas in your sample, there's going to be a major change in the volume. Because if you produce a mole of gas, let's say at STP, what's the volume of a mole of gas at STP? 22.4 liters. That's a big change in volume. So when we did the earlier example with water, we just have changing the temperature, though it stayed a liquid. Okay, the liquids and solids don't change very much in terms of volume when you change the temperature. Okay, but anytime you have a process where a gas is involved, if there's a change in the temperature or you have a reaction that produces a gas, okay, there's going to be a significant change in the volume. And pretty much you can ignore the changes in the volume of whatever solid or liquid you have there. You can just ignore the solids and liquids. The change in the volume will be pretty much the change in the volume of the gas. Okay? So if the volume of the gas changes, how do you calculate that from your ideal gas equation? P delta V, okay, would be due to a change in the number of moles of gas. Delta N gas times RT. Okay? So at constant pressure, the change in the volume would be just delta N gas RT divided by P. So P delta V will just be delta N gas times RT. And so we use that to answer this question here. We have a reaction, okay, and it produces half a mole of gas. So if you have, imagine you have, okay, a reaction mixture here, okay, it's gonna push up that wall to generate the gas, the half a mole of gas. It will expand, okay. So what would be the work involved here? Work will just be negative. Change in moles of gas in this problem is given as half a mole. So 0.500 moles of gas times RT. What is RT? RT is 0.08206. Remember your R from ideal gas law? Liter atmosphere per mole per Kelvin times, what's our temperature? 298 Kelvin. Okay? So if you did this, what would your answer be? What would be the units for your answer? Kelvin cancels out, mole cancels out. You'll have your answer in liter atmosphere, right? But if you want your answer in joules, what would you have to do? 1 liter atmosphere is 101.325 joules, right? So you multiply this by 101.325 joules for 1 liter atmosphere. Okay? So you can change your R in joules, okay? Look at this. 0.08206 times 101.325, that's 8.314, okay? So a more convenient unit for R, a convenient number to use for R, oops, what did I just do? Would be to use 8.314. So we can say this is negative 0.500 moles times R, which is 8.314. If you want your answer in joule, might as well use this value for R, okay? So R, these are two good numbers to remember for R. It's 0.08206 liters times atmosphere per mole per Kelvin. And a liter atmosphere is 101.325 joules, so that's equal to 8.314 joules per Kelvin per mole. Okay, so multiply that by 8.314 joules per Kelvin per mole, and our temperature is 298 Kelvin. So mole cancels out, Kelvin cancels out. What would that give you? So our work is equal to negative 0.50 moles times RT. That's 8.314 times 298. That's 2477 joules. Okay, so 2.477 joules. 2,477 joules. Okay. There's no units have canceled out, right? So 204.77. Yeah, it's joules. Okay. So work would be half of that. So 2477 times 0.5, that gives you 1,238. So 1.23, 1.24 times 10 to the third joules. Okay. Or negative 1.24 kilojoules. So that's the amount of work. Okay, so you can see that's not negligible compared to the previous numbers that we've been dealing with. Okay. Now this expression RT occurs very often in our calculations. So it's a good thing to remember that a ballpark figure for that is what? What's a ballpark figure for RT at room temperature? 2477. That's about 2500 joules. So that's 2.5 kilojoules. Okay. So this is approximately right here. This is approximately 2.5 kilojoules. That's a good number to remember. Okay. That's 2.5 kilojoules per mole. You're going to encounter that a lot. So if you want to be able to quickly ballpark a number, think of that as an estimate. Okay. It's 2477 joules. All right, so let's look at this one. You have a hypothetical reaction where you have 2A solid plus 2B gas yields a mole of gas C. So that means for every mole of C produced by this reaction, how much work is involved? Again, if you have a reaction, it involves gases. The change in volume will primarily be due to the change in the moles of gas. Okay, so minus P delta V, or you can say that's negative delta N gas times RT. So what's delta N gas here? If I make a mole of C, what's my delta N of gas? How many moles of gas do I have on the product side? Coefficient is 1, right? How many moles of a gas do I have on the reactant side? 2, because A is a solid, B is a gas. So 1 minus 2, that's negative 1. In other words, what this balance equation is telling me is that every time I make a mole of C, I'm going to lose 2 moles of B, right? So I'm going to be losing 2 moles of gas. As this reaction progresses, every time I make a mole of gas, I'll lose 2 moles. So I end up with a net loss of 1. So will this system be shrinking or expanding as the reaction goes? It's going to be shrinking. Delta N gas is negative, right? So your delta V here is going to be negative, so your work is going to be positive, right? And let's see if we do get that. Delta N gas is negative 1 mole, right? That's your delta N gas. It's negative 1 mole. What's our RT? What was our ballpark figure for RT? 2.5 kilojoules per mole, right? I'm just estimating here. So that would give you positive 2.5 kilojoules per mole. Mole cancels out. So positive 2.5 kilojoules. So that's the amount of work. Okay? So as this reaction progresses, your system is going to be shrinking. You're going to be replacing 2 moles of gas by 1 mole. So fewer gas is going to shrink. That's going to be a big change in the volume. How about this one? Let's say 0.2 moles of B is consumed in this reaction. Okay, what would be the work? If I lose 2 X moles of B, how much of C would I make? I'm going to gain X moles of C, right? So what will happen then? If 2X is equal to 0.2, what is X? 0.1, right? You got it? So you're losing 2 moles of B, and you'll make a mole of C. So if you lost 0.2 moles of B, you're going to make 0.1 moles of C. So if you lose 0.2 moles of B, you're going to make 0.1 mole of C. What's the net change? What's our delta N gas in this case? I make 0.1, I lost 0.2. But how much did it change? There's a net loss of 0.1 mole of C, right? So your work in this case would be what? Work would be equal to minus delta N gas times RT. So it's going to be negative of 0.1 mole times RT. And what was our estimate for RT? At 298 Kelvin. That's about 2.5 kilojoules per mole. So mole cancels out. So you're going to have, I'm sorry, that's negative 0.1. So that becomes positive 0.25 kilojoules. Okay? System is going to shrink, not as much as the other case. Here you actually have a loss of a mole in the earlier question. In this question right here, you only lost 0.1 mole of gas. Right. Summary with PV work. Okay, PV work is negative P external times delta V. If the system expands, PV work is negative. If system compresses, shrinks, work is positive. Okay, unit for work is liters times atmosphere, which is equivalent to 101 joules. Okay, 3 sig figs, you can just use 101 joules. When you're dealing with liquids and solids only, the pressure volume work tends to be very small compared to the heat. Okay, so most of the time we can just ignore the amount of energy transferred due to work if the only thing you're dealing with are solids and liquids. But if there's reactions that involve gases, or okay, if you're involving gases in this, gases are involved in the changes you're looking at, then you have to worry about the work involved, the energy transfer due to work. So PV work, when there's a change in the moles of gas at constant pressure, is negative of delta N gas times RT. So your R is 0.08206 liter atmosphere per mole Kelvin, or if you want to go straight to joules, that's 8.314 joules per mole per Kelvin. Okay. I gave you a ballpark figure of 2.5 kilojoules for RT at room temperature. Okay, 2.48 would be a better. If you want 3 sig figs, you can use 2.48 kilojoules per mole. Okay, this is really per mole. Okay, so that's the summary for work. Now let's talk about the first law of thermodynamics. Okay. The first law of thermodynamics says every system has a property called internal energy. It has a state function. Okay. What did we say a state function was? It's a property of a system that is well defined at equilibrium. And we say every system has what we would call internal energy. And this internal energy changes when the system undergoes a change. Okay. And so we represent that change by delta E. Okay? And what we're saying is, the first law says delta E is equal to Q plus W. What that means is this. If a system undergoes a change, okay, from one equilibrium state to another, then if you add up all the Q's and the W's that are involved during that change, that will give you the change in the internal energy. That will give you delta E. So if you want to know what the change in the internal energy is, just look at how you got from your initial state to your final state, calculate all the Q's, calculate all the W's, add them all up, you get your delta E. Okay? So Q is the energy transferred due to heat, okay, and W is the energy transferred due to work. So that's the first law of thermodynamics. What it's saying really is this. Because it's a state function, it doesn't really matter how you get from your initial state to your final state. Remember we said heat and work are path functions? They depend on how you get from your initial state to your final state. So it matters. Okay? Heat would be different depending on, you get different values of heat depending on how you got from your initial state to your final state. Work varies according to how you get from your initial state to your final state. But if you're looking at the same initial state and your final state, even though you have different ways of getting there, if you add up all the Q's and the W's, you'll end up with the same answer. Okay? Q and W depend on how you get there. But if you add up Q and W, it doesn't matter how you get there. Okay? So that suggests then that Q and W must represent a change in some state function, a change in some property of the system, and we call that property of the system internal energy, because we've already associated the idea of energy for heat and work anyway, right? So The first law can also be stated as simply the law of conservation of energy. It's really nothing more than saying that energy of the universe is constant. Okay? It's a law of conservation of energy because by definition, how did we define heat and work? Heat and work we define as just energy, that's something that's transferred from surroundings to system. So what we're really saying is energy is just being transferred in the universe from one place to another. It doesn't, you don't, it doesn't, you don't destroy it, you don't make it, you just transfer it from one place to another. Okay? So energy is neither created nor destroyed. How do we know this is true? Well, all our attempts to produce energy out of nothing have failed. Okay, so that is and it's because that is an assumption that would be consistent with everything else. So that's the law of conservation of energy. So the first law can also be stated by saying that the total energy of an isolated system is constant. What's a system that's isolated? One that doesn't interact with the surroundings. So Q is 0, W is 0. Okay. Anything could be happening within your system, okay, but if it doesn't interact with your surroundings, Q is 0, W is 0, its total energy would be 0, will not change, so delta E will be 0. So you say the total energy, total internal energy is constant. Okay? Since the universe, you can think of the universe as everything, right? We can think of the universe then as an isolated system, then you can also state the first law by saying the energy of the universe is constant. Okay? You don't create or destroy energy, you just transfer it from one place in the universe to another. Okay. Sign conventions for delta E follow the sign conventions for Q and W. So remember we said Q and W are positive if energy flows into the system, otherwise it's negative. So delta E is the same thing, okay? It's positive if there's a net increase in the energy of the system, then you would expect delta E to be positive. If there's a net decrease in the energy of the system, you expect delta E, the final E, to be less than the initial. So delta E in that case would be negative. Okay, let's do a few concept tests here. Let's see if you got the concept. A system absorbs 10 joules of energy. What's delta E? Okay, there's no clicker here. This is going to be plus 10.0 joules, right? What's the delta E for the surroundings? If 10 joules went into the system, where did it come from? So what happened to the surroundings? It lost 10 joules. So delta E for the surroundings is negative 10.0 joules. What's delta E for the universe? It's always going to be 0, right? The energy of the universe is constant. Okay? So how about this one? A cyclic process. Okay, we say a system undergoes a cyclic process. If it goes through a series of processes where it eventually returns to its initial state. So the final state is the same as the initial state. So you can take a system through a series of changes and eventually you get to a final state where it was just like it was originally. What would be our delta E? 0, right? Because E final would be the same as E initial. We say energy is a state function. So delta E, in other words, if you were to add all the Q's and the W's for all the processes you went through, all of those Q's and W's are going to add up to 0. What would be their delta E for the surroundings? 0. And delta E for the universe? 0. Here's a question. A system goes through the following processes. It goes through step 1. Q for step 1 is 5 joules. That means 5 joules went into the system as heat, and the system did 8 joules of work. So W is negative 8 joules. Step 2, Q is 15 joules. W is 5 joules. So in step 2, the system did work. Lost 15 joules, gained 15 joules of heat, and it absorbed 5 joules of work. Okay? 5 joules of work was done on it. What's delta E for the overall process? 10? Okay. What do you do to get delta E? Just add up all the Q's and the W's. So what's 5 plus 15 plus, so that's 20, right? 25 plus negative 8, what would that be? 17 joules. Just add up all the Q's and the W's. Okay? What's delta E for the surroundings? Negative 17. Whatever the delta E is for the system, that would be the opposite for the surroundings. What's delta E for the universe? 0. So do you want one question on the test that asks for delta E of the universe? All right. A system goes through the following processes. Step 1, it went from state A to state B, and then step 2, it went back from state B to state A. Okay? So it goes through a series of processes from A to B, and then went back from B to A. Q for step 1 is 5 joules, W is negative 8. Okay? And step 2, Q is 15. What's delta E for the overall process? It goes from A to B and back to A. What's delta E? 0. Don't be tricked into just adding Q's and W's, okay? Because you're missing some information here. You're not told what the W is for this step. A lot of students get tricked by this type of question because they just remember delta E is Q plus W, so they see all bunch of Q's and W's, they just add them up. Okay, you have to realize if you're doing a cyclic process, delta E is 0. So in fact, if you add all of these Q's and W's, they're not going to add up to 0. That means there must be a missing information here. Okay, delta E of surroundings is how much? 0. Delta E of the universe? 0. What's W for step 2? Negative 12. Let's see. 5 plus negative 8 plus 15 plus W2 would be equal to 0. All of that should add up to 0, right? It's a cyclic process. So what would this be? 5 plus 15 is 20 minus 8, so that's 12 plus W2 is 0, so W2 is negative 12.0 joules. Okay? So what's the molecular interpretation of internal energy? It's really nothing more than the energy of the atoms and molecules in your system. Okay, so it's a sum of potential energy, which depends on how they're located, where their positions, their relative positions, plus their kinetic energy, energy due to motion of atoms and molecules. Okay, so if your system does not interact with your surroundings, your internal energy is just constant. Okay. It's just by themselves. So any changes in potential kinetic and any change in potential energy just becomes a change, the opposite change in kinetic energy. Now, Q, okay, is the energy transfer due to heat flow that results from random collisions among atoms. Okay, so a hot and cold object in contact will eventually reach the same temperature because of these random collisions between the atoms. Your energy just gets redistributed. So it's random redistribution of energy. That's what heat flow is all about. Atoms in contact, they're always moving, they collide with each other, they just spread, the energy just spreads out. That's just the natural tendency for energy to just be dispersed. Okay? Work, on the other hand, oops, it's almost time to go. Let me just finish this. I've got a couple more slides. Okay? So let's look at this one. Adiabatic walls, we said, would be thermally insulated walls, right? They don't allow heat to flow between system and surroundings. An example of an adiabatic wall would be your thermos bottle. What do you have inside that thermos bottle? There's a vacuum in there. So why is it very good for insulating? Making things cold, keeping things hot. It doesn't transmit heat very well. Why? If there's a vacuum there, there's no atoms that can collide, and so see, heat transfer occurs due to collisions between atoms. So if there's no minimal collisions between atoms, then there's minimal heat transfer. Okay, so that's how a thermos bottle works. Styrofoam. What do you know about styrofoam? It's very light, right? There's a lot of air pockets in your styrofoam. So what do you know about gases or air? The molecules are far apart, so You're trying to minimize collisions between the atoms there. That minimizes the ability of your material to conduct heat. Okay, so that's how they work at the molecular level. What about work? Work, the way you interpret work is that that's the energy transfer that results from a concerted or a synchronized or an organized motion of atoms. Like when you squeeze something, the atoms in the wall are all moving in concert, you could say. Okay, it's not just a random collision. So it's collisions that results from a concerted motion of atoms. So that could lead to collisions and redistribution of kinetic energy among the atoms, and so that's how you transfer energy by work. Okay, and I think that's the last of the slides. Thank you.